today we will clearly understand what a linear transformation is. A linear transformation is a function that takes vectors as input and produces new vectors as output, but it must follow two very important rules. Rule 1. If you add two vectors first and then apply the transformation, it must give the same result as transforming each vector separately and then adding the results. In simple words, the transformation must preserve addition. Rule 2. If you multiply a vector by a number first and then apply the transformation, it must give the same result as transforming the vector first and then multiplying the result by that number. This means the transformation must preserve scalar multiplication. If both rules are satisfied, the function is a linear transformation. Now let us see how matrices are connected. Every linear transformation in two dimensions can be represented using a matrix. If A is a 2 by 2 matrix and X is a vector, then applying the transformation is the same as multiplying the matrix by the vector. So matrix multiplication is just a machine that performs a linear transformation. Now let us understand the geometric meaning. Linear transformations change vectors in structured ways. They can rotate vectors. They can scale them, meaning stretch or shrink. They can shear them, which means slant them sideways. They can reflect them across a line. They can even project them onto a lower dimension. But they always keep straight lines straight, and the origin always stays fixed. Let us see some examples. Example 1, rotation by 90 degrees. There is a specific matrix that rotates every vector by 90 degrees counterclockwise. If you apply it to the vector 1, 0, it becomes 0, 1. If you apply it to 0, 1, it becomes minus 1, 0. So the axes rotate perfectly. Example 2, scaling. If you multiply both coordinates of a vector by a number k, then every vector stretches by that factor. If k is greater than 1, the vectors become longer. If k is between 0 and 1, the vectors shrink. If k is negative, the transformation also flips to. Now let us talk about determinant. The determinant of a matrix tells us how areas change. If the determinant is 2 areas, double. If the determinant is 1/2 areas, shrink to half. If the determinant is 0, everything collapses into a line or a point. If the determinant is positive, orientation is preserved. If it is negative, orientation flips. So determinant controls area scaling and orientation. Now let us understand kernel and image. The kernel of a transformation is the set of all vectors that become 0 after transformation. These vectors completely collapse. The image of a transformation is the set of all possible output vectors. There is an important theorem called the rank nullity theorem. It says that dimension of the kernel plus dimension of the image equals the dimension of the input space. This is a fundamental result in linear algebra. Now, some key properties. If you apply one linear transformation after another, the combined transformation is still linear. Its matrix is the product of the two matrices. A linear transformation has an inverse only if its determinant is not 0. Eigenvalues and eigenvectors are special vectors that only get scaled but do not change direction. Every linear transformation always maps the 0 vector to the 0 vector. The origin never moves. A linear transformation preserves addition, preserves scalar multiplication, can be represented by a matrix, changes geometry in structured ways, and has deep connections to determinant eigenvalues and vector spaces. In this exploration of linear transformations, we see how they alter geometric shapes while preserving certain properties. The relationship between the associated matrix and its determinant plays a crucial role in determining the invertibility of such transformations. As we visualize eigenvalues and eigenvectors, their unique characteristics become evident, offering insights into the structure of vector spaces.